Welcome to Systems Design. If you're watching this the first time, I'm assuming that you have just completed the data structures and algorithms part of the curriculum, and you're familiar now with the basics of data structures and algorithms. So let me set the stage for a smooth transition to systems design by explaining what exactly changes when we move from data structures and algorithms to systems design. So in the data structures and algorithms part of the curriculum, you are typically given a computational problem, a question that you have ideally not seen before, and you are expected to use some of the problem solving strategies or algorithm design strategies to design a correct and efficient algorithm which solves the given problem. And then, assuming that the interviewer agrees that what you have designed is a correct and efficient algorithm, the second part of your job was to then code up the algorithm that you have just designed. It was implicitly assumed that the function or program that you have written would be called by some user, maybe the interviewer who's standing or sitting next to you, with specific inputs or parameters to your function. These would be the various test cases. And then your program or function was supposed to generate a specific output, a specific return value or a set of return values, after which it would halt. Your program obviously used some resources like CPU and RAM to solve the problem, and how much CPU it used was quantified as the time complexity of the algorithm, and how much RAM space it used was quantified as the space complexity of the algorithm. And RAM in particular was assumed to be unbounded or infinite in size, which is why in asymptotic analysis we assumed that the input size, the size of the input, which was denoted as a variable, something like n, could grow in an unbounded fashion. As the input size became very large, we tried to quantify the rate of growth of the running time and the space used as the time and space complexity of your algorithm. So when we solved the sorting problem, we assumed that we had one single machine on which our program was running, one single CPU, and our data or input array was entirely in RAM. And under those conditions, we said that an algorithm like merge sort would take time order n log n in the worst case. This is the number of elementary operations that the algorithm would execute on the CPU. And we said that the algorithm needs order n auxiliary space in RAM in order to execute. In systems design, we now want to convert our standalone program into an online service. So imagine now the users of your program as residing far away from you. They want to execute your program remotely over a network. They will send a request to your machine to run the program using the input parameters that they are sending over the network. Your program will run on those inputs, and then you'll need to send the output back to them as a response over the network. So we're going to see how to build such an online service. How do we convert our lead code style program into an online service? Let's clarify some terminology here. We're going to call our program as an application program, or an app in short, to distinguish it from a program that supports the operating system software. So in contrast to those system programs which support the OS software, our application program directly meets the functional needs of a user. And we call the program as an online service because it offers a service over the network. It accepts an incoming request. It forms a response by calling your lead code program with the client input, and then it returns the result to the user. The machine that runs our online service is going to be called a server, and the user is obviously going to use a machine to send in the request. So the user program or user application, which is actually sending the request to our server program, waiting for a response, and then getting back the response, this user program is called a client. For example, the client program could be a browser that is requesting a copy of a web page. The server in this context would be called a web server, which will look up its file system and take the requested page and send it back. There's not much logic involved in returning the response here. It's not as if the server program is solving a hard puzzle problem like a lead code problem, but we'll see examples later where the server program is more sophisticated and employs some sophisticated logic. So whatever we learned in data structures and algorithms will come in handy at that point. Now, one difference between the client and the server programs here is that our server program is always actively listening for new client requests. It is always on. It's running this infinite while loop, conceptually speaking. It accepts the next incoming request, runs your lead code program, generates the return values and returns those values to the user, and then it goes back to listening for the next incoming request from the next client. So it's always on, it's never turned off. The client program, on the other hand, usually terminates after getting the response back. At least that's the way we conceptually look at it. Now, if I'm this client looking at this server, I don't see the code that this server is running. I just look at the server as a black box, or a white box in this case, and all I see is this interface in front. This is the public interface that is visible to me as the client. The internal implementation of how exactly my request will be satisfied, the code for that is not visible to me. Now this interface, this public interface, is in general known as an application programming interface, or an API, and it essentially exposes to me as the client the overall behavior of this online service while keeping the code private. So the API tells me what kind of requests I can make, what is the data format in which I should submit those requests, what the overall behavior of this online service is, and in what format the response is going to be returned, and what are the semantics of that response. For example, if I requested a web page and this web server couldn't find the web page, then it might return back an error in its response with an error code like 404. The semantics of this number 404 is that the web page that I had requested for was not found by the server. Now the code that we write for implementing this online service could be very complicated. It need not be as simple as writing the code to solve a lead code problem. It could involve tens of thousands or even millions or tens of millions of lines of code. It might be impossible for one single person to implement that online service. So when the overall service is too complex to implement by one single person, we might imagine it as being composed of a bunch of smaller sub-services or microservices which are interacting with each other to somehow provide the overall service that is expected at the application programming interface level. And that leads us to the definition of a system. So what do we mean by a system or a computer system specifically? Well, a system is nothing but a set of components which interact with each other to provide some kind of overall functionality at its interface. So a system has an interface which separates it from its outside. So everything outside the system is what we call the environment. And so you can think of any system as a black box exposing an interface. And inside this black box, there might be a collection of components which interact with each other to provide that functionality. Now, each component here can be thought of as a subsystem, right? So the definition kind of becomes recursive. In order to define a system, we are saying it's composed of a set of interacting components, but then if we ask what is a component, well, it looks like it's a subsystem, and then how do we define a subsystem? So we can keep zooming in inside each of these components or each of these subsystems, but at the base case, at the basic level, every computer system, at least for our purposes, is going to be composed of three types of atomic units. There's CPU, then there is memory, which could be either RAM or disk, and then there are communication channels which link together the compute resources like individual CPUs and the storage resources like RAM or disk. So CPU, memory, and communication links, these are the atomic units out of which any computer system is built. In other words, CPU, memory, and communication links are the smallest systems that we can imagine as far as systems design is concerned. Now we can again zoom into them, and we would see hardware resources, we would see transistors, we would see atoms and subatomic particles, but those details are not relevant to us when we are doing systems design for a software engineering interview. We stop as soon as we get to these atomic units, CPU, memory, and communication links. Now, if we think of the CPU itself as a tiny system, it has the ability to execute primitive assembly language instructions. So if I give it two numbers, for example, it can compute their sum and return the sum, or it can compute their difference, product, quotient, and so on, or it can do Boolean operations on them. So we will look at the CPU as the most elementary computing system. Now, memory as a storage system at its most basic level allows us to take data that we are sending to it, and it will store that data, and then if we want to read that data, we can read the data that was previously written into memory. So it provides a storage service at its interface. Now, when we look at a communication channel, what kind of service does a communication channel expose? Well, if you give it a stream of data, say a sequence of bytes, the communication channel will ensure that the sequence of bytes gets across or is transferred to the other end of that channel. It could be as small as a system bus that transfers the bytes from CPU to memory or vice versa, or it could be a long network channel which transfers the data from one machine in one part of the globe to another machine in a different part of the world. So any larger system, like an individual computer, for example, is built out of individual CPU, memory, and communication channel components which are linked together in fairly complex ways in order to build that machine. And when it comes to larger scale systems of the kind that we're going to look at in this course, we might have several machines, thousands or tens of thousands of them, which are linked together with communication channels, and each machine could have multiple CPUs and multiple RAM chips and disks inside them. But collectively, all those machines interact with each other to provide and expose an overall functionality to the end user. So that would be an example of a system that is much larger in size than a single machine. Now, any online service system that we build needs to be able to generate the response that the client is expecting in a fairly short amount of time. In other words, the response time, which is the time that elapses between the client sending the request and getting back the response time has to be kept as small as possible. And the challenge is that as our online service becomes more and more popular, there'll be more and more clients that will be sending requests to our server and expecting a response back quickly. So if our online service can handle a large increase in the traffic, in the load or the number of requests that are coming in from clients per second, if our system can handle that fairly well, then we call that kind of system a scalable system. And in this course, we are interested in understanding how we can build scalable systems from first principles. Online processing systems are not the only type of systems that we want to scale. We will look at other types of systems as well, but we are going to start with online processing. And we are going to assume a client-server model of interaction between different applications.